Okay, the next topic I'm going to talk about is measuring speed, and this is going to be a lead-in to our study of differential calculus and the notion of a derivative. So the first thing I'd like to introduce is the concept of average velocity. So probably many of you have seen how to compute this before, but I'll quickly explain this. So suppose d of t gives the position of an object at time t. And suppose we want to find the average velocity between 2 points in time, t equals a and t equals b. So we have a formula that allows us to do this. So the average velocity, which I'm going to note by v with a bar over top, is equal to this distance function at b minus the distance function at a divided by the difference in the time points, b minus a. So for example, suppose we have some car driving along the x-axis and its coordinate on the x-axis at time t is given by t squared plus 1. And we want to find the average velocity between t equals 2 and t equals 4. So the way we would do this is to plug in to our formula here. So in this case, b is equal to 4, a is equal to 2, and instead of calling my function d, I've called it x, but that doesn't really matter. So v bar is going to be equal to x of 4 minus x of 2, all divided by 4 minus 2. If we plug in 4 to this equation for x, then we'll get 64 plus 16 plus 1, that's x of 4. Then we have to subtract x of 2, which is 8 plus 4 plus 1, and divide by 4 minus 2 still. Then, let's see, this gives us 81, this gives us 13 over 2. And if we simplify that, we'll get 68 divided by 2, which is 34. So this is our average velocity on that time interval. Now, this calculation, doing a change in the output of the function divided by the change in the input, might remind you of calculating the slope of a line. And that's because it's basically the exact same calculation. And that's a useful way to think about this because it gives us a graphical interpretation of average velocity. So if I have some function d of t, so the x-axis will be t in this case, and the y-axis will be d of t, and we have our 2 points a and b. Then the slope of the line connecting these 2 points is going to be exactly equal to the average velocity. And this line connecting the 2 points on the curve has a name. It's called the secant line. So what you'll notice is that at the start of the interval, the graph is not going up as fast as the secant line is increasing, right? Because they start at the same point, but the line ends up going above the curve. So actually at the start, the object is not moving as fast as its average velocity. But then eventually it has to start moving faster so it can catch up to the line. And so over here, the object is actually moving faster than its average velocity. But when we average the two things together, we get the slope of this line. So this discussion, though, does reveal a downside of average velocity, which is that it only gives us some average notion of how fast the object is going. So for example, suppose we have two curves. One is just an object moving at a constant velocity, so that would be this straight line. But then the other one is something which moves really, really fast at the start and then starts moving more slowly for the rest of the time interval. So if we look at the average velocity between 0 and this point out here, I'll call it A, then we get the same value for both of these curves. I'll call this one D1 and this one D2. But, for example, if these curves represent speeds of cars, then D1 was maybe going at the speed limit the entire time, but D2 was actually speeding at the start, even though the average velocity was the same because D2 slowed down a lot after this point here. So if you want to say a cop pulls this car over and asks, you know, were you speeding? Well, we can't just look at the average velocity because the average velocity for D2 was exactly the speed limit, but we have to look at how fast the car was moving at this point over here because that's where it was moving really, really fast. So we like to have some notion where we can discuss how fast something is moving at a single point rather than an average speed over an interval. And we can do that using a notion known as instantaneous velocity, which tells us how quickly an object is moving at a single point in time. So average velocity was the slope of this secant line. The instantaneous velocity should sort of be telling us how quickly the function was going up at this moment. And you can sort of imagine if the function hadn't started curving downwards and just had kept going really, really fast, then it would have looked something like this for the graph, or just keeps going up at that same really fast rate. And this line, which sort of touches the graph at this one point and then just keeps going up at the same rate, is known as the tangent line. And the slope of the tangent line is going to be equal to the instantaneous velocity at that point. The problem that we have is that we could find the slope of the secant line because we were given 2 points on the line, 0 and A, and we knew the position at those 2 points. The tangent line, we only know 1 point. We know this point here. We know no other points on the line, so we have no way of actually finding the slope of this line. So this is a problem, and we need to think about how to get around that. So it turns out there's a clever way we can get to the slope of this line without ever actually knowing another point on it. So let's redraw our graph here. So let's draw some function, maybe something like this. And suppose that I want to find the instantaneous velocity at this point at t equals a. Well, I don't know how to find the slope of the tangent line here, but if I pick some other point on the curve, let's call this, maybe it's a plus 1, well, I can certainly find the slope of the secant line connecting those 2 points. But this is not going to really tell us anything about the instantaneous velocity here. But now let's suppose I look at a plus 1/2. I can find the slope of this secant line, and it sort of visually looks like it's a little bit closer to how quickly the function was going up exactly at a. Now if I look at, say, a plus a fourth, I have this secant line here, and now it looks very close to what we expect the tangent line to be. So if I redraw this graph over here, remember that the tangent line at that point will look something like this. And if you compare this one to what we get over here for this secant line between A and a point really close to A, they look pretty close. So the idea is that we can approximate instantaneous velocity at t equals a by the average velocity from t equals a to t equals a plus h. And so, okay, what is the formula for average velocity on this time interval? Well, we can write it down. It's going to be d of a plus h minus d of a divided by h. Okay, maybe I should write another step here. It's a plus h minus a, then the a's will cancel out and we'll just get the h in the denominator. So I said this is an approximation. How can we get a better approximation? Well, if we look back at our graph, we did this by moving the point a plus h closer and closer to a. So we let the number h that we were adding to a get smaller and smaller. We can represent that mathematically with the notion of a limit. So v, which is going to be the instantaneous velocity at the point A, is going to be equal to the limit as h gets closer and closer to 0 of this thing here, d of a plus h minus d of a divided by a plus h minus a, which is equal to the limit as h goes to 0, d of a plus h minus d of a over h. So we're calculating instantaneous velocity by taking the limit of the average velocity on smaller and smaller time intervals near the point A. So let's look at an example. Let's suppose that we want to find the instantaneous velocity at t equals 2 for a car whose position at time t is given by d of t equals t squared plus t. How can we do this? Well, if we use our formula up here, we have v is equal to the limit as h approaches 0, d of 2 plus h minus d of 2, all divided by h, right? So a is the point where we want to find the instantaneous velocity, so in this case a is equal to 2. Now the next step, if we want to find this limit, you might think, well, our first thought is can we plug in h equals 0? But if you do that, the denominator will be 0, the numerator will also be 0, so that doesn't really tell you anything. So instead what we need to do is first simplify this expression, see if somehow we can get rid of this h in the denominator that causes trouble. So let's start by plugging in 2 plus h to our formula for d of t. So we have 2 plus h squared plus 2 plus h minus d of 2 gives us 2 squared plus 2, all divided by h, and we still have a limit as h approaches 0. Now, if you expand out this square, then you'll get limit as h approaches 0, 4 plus 4h plus h squared. That's from this first term. Then we still have the plus 2 plus h. And then this, if you simplify it, will be minus 6 divided by h. And now we can see there's some more simplifications. We have 4 plus 2, but then minus 6, that gives 0. We also have a 4h plus h, gives us 5h. So we have limit as h goes to 0, 5h plus h squared over h. And now, the nice thing that happens is we can see there's an h in everything, so we can cancel an h. And we're just left with limit as h goes to 0, 5 plus h. And now we can plug in h equals 0, since this is just a nice continuous function. To get the value of the instantaneous velocity is 5. So this is the method for how you can calculate instantaneous velocity. We'll see a lot more examples of this because we'll find that this calculation is just a special case of what's known as the derivative of a function, which we'll see in the next lecture.